In this video, I want to talk about some applications that we can do with oblique triangles and the law of sines as well. So the first thing is the area of a triangle. Now, most of us know the area of a triangle is 1/2 base times the height. But that really applies when you have the height coming down. So typically we end up using this for right triangles. You can use it for other triangles too, let me say, but you have to have that perpendicular height. So there has to be some sort of right triangle in there somewhere that you can go ahead and use this formula with. Like I said, you may have seen it with other triangles, but you do have that height. So you'd have to have that height piece, which makes a right triangle. If you don't have a right triangle or a right angle somewhere in there, there is another formula that you can use, and that is valid for oblique triangles, where again, you don't have that height feature. So maybe it's not given, or maybe you can't find it right now. And you can use a different formula. So that formula is 1/2. And what you do is you multiply 2 of the lengths and you multiply by the side of one of the angles. But the key thing here is that these are all different. So the 2 lengths that you use would be different than the opposite angle. So notice here you're using lengths A and B and then angle C. Here you're using lengths A and C and angle B. So it's always 3 different parts of that triangle. So let's do an example. We're going to find the area of a triangle that has sides 24 meters and 10 meters and an included angle of 62 degrees. So I'm going to draw a picture first, and again, it's not going to be to scale, so bear with me. Let's see, one of my sides is definitely shorter than the other, so I don't know, maybe something like this. Not quite sure. So here's my triangle. Let's say that this is the 10-meter side. Let's say that this is the 24-meter side. Now, when we say an included angle, it means in between the 2 lengths. So the angle that we know is this one right here is 62 degrees. Again, not drawn to scale. It looks more like a right triangle, but it's supposed to be 62 degrees. But the big takeaway here is when you see included angle, it means in between the 2 lengths. Which is important. Okay. I'm just going to label everything just to help myself. And again, it's a bit arbitrary. It doesn't actually really matter where I start my angles as long as I have everything organized and the angles are across from their associated lengths. So A across from little a, C across from little c, B across from little b. So notice here, I know my length for A, I know my length for B, and I know my angle for C. So I have exactly what I need. I should have an A, B, and C for each piece, but again, all different. 2 lengths, 1 angle. And really, these are all the same formula. It just depends how you label them. So here we're looking at this formula right here. So 1/2 AB sine of C. A is 24, B is 10. And then sine of 62 degrees. This is going to be half of 24 is 12 times 10 is 120. So it's 120 times the sine of 62 degrees. And again, you can go ahead and use your calculator here, and you should get about 106. Again, we're rounding to the nearest whole, the nearest square meter here. So our area is about 106 square meters. Okay, and again, you're just doing that last piece right there on your calculator. 120 times sine of 62, and you can see that rounds to 106. All right, I'm going to do one more application here, and then we'll wrap up this section. So let's say you have 2 fire lookout stations. And they are 20 miles apart. With station B directly east of station A. So for instance, let's say here is station B, and then station A would be right here, right? So here's station B, here's station A. Oh, other way around, sorry, I was doing west. There's A, there's B, let me fix that. So station B is east of A, excuse me. So here's A, east is going towards the right, so station B would be on the right. And they are 20 miles apart. Now, we also know that both stations spot a fire on the mountain to the north. The bearing from station A to the fire is the following. So it is north, 50 degrees east. And then the bearing, I'm gonna have to redraw my picture a little further down. From station B to the fire is, let's see, north, 36 degrees west. And our question is, how far to the nearest 1/10 of a mile is the fire from station A? So how far is fire from station A? All right, so let me redraw this picture so I have more room. So here we have station A, here we have station B. Now they both see a fire north in the mountain, right? So maybe the fire is right up here. They both see this fire. Now from station A, the bearing is north 50 degrees east. Now think back a few videos here. With bearings, it's always off a north-south line. So like a straight up and down line, right? This is your north-south line. And it's 50 degrees east. So that angle there is going to be right here. This is your 50 degrees, again, off that north-south line and going towards the east. On the other side, you have 36 north, 36 degrees west. So again, you have your north-south line. And again, we're going towards the west off the north line, so west. And then your angle here is 36 degrees. I know these are not to scale, so, you know, kind of bear with me. Let me connect these with my fire. So let's say this is my angle right here. And this is my 36-degree angle right here. Connecting those with the fire. We want to know how far is the fire from station A. So we actually want to know this distance right here. That's really our question, right? How far is it from station A? And if you can see here, I end up drawing a triangle. Now let's figure this out for a second. So if this is 50 degrees and this is a right triangle here, right? A perfectly 90-degree angle, then this side must be 40 degrees to get 90 degrees. Over here, this would be a 90-degree angle, the whole thing together. So, you know, 90 minus 36 is going to be 54 degrees. So this is 54 degrees. So we can find those missing pieces. Now I can also find the other angle if I want to by using 180. So this would be 86 degrees. I also know that this here was 20 miles. Okay. So I filled in my triangle as much as I can, kind of just initially with some quick math. And now I need to actually find this length. This is what I want right here. So let's line everything up. If this is AB, let's call the fire C. So this is C. And this is B. So we're looking for the B piece here, not necessarily the A. Now I need one complete ratio if I'm using law of sines. So one complete ratio is the C's, right? I have both the length and I have the angle. And then I'm looking for B here. So that's what I really need to focus on. So B over sine of B. So let's see, I have 20 over sine of 86 degrees equals B over sine of 54 degrees. I'm going to go ahead, I'm going to multiply both sides by sine of 54 degrees. And again, you're just going to use your calculator here. It's 20 times the sine of 54 degrees all over the sine of 86 degrees. And when you use your calculator and you round, you get about 16.2. And we'll stick with the nearest 10th here like we have been. And just watch your units. We were given miles. So this is going to be 16.2 miles. So the fire is approximately 16.2 miles from station A. That was the question we were answering. Again, everything is approximate because you are doing a lot of rounding here, right? We're using our calculator and we're rounding our final answer, but it should be very close, right? So it's about 16.2 miles from station A in this case.